I want to record this one. Okay, so page 5, this again, we're up in the level, so it's not a standard cookie cutter, so slow down, okay? I know that AP exam is a time test. I know that you're stressed and pressed for time, but don't read too quick. Don't make assumptions too quick, okay? And so notice we have a graph. Now we're not going to have to graph any, they're giving us information on the graph. Always know what's being plotted. Now, because this is a teacher-made graph, okay, they just put a title. And just FYI, physics graph titles are not creative like some, biology graphs, but we put them in terms of whatever's plotted on the y-axis versus whatever's plotted on the x-axis. And it tells us that in the reading, but that 1, 2, 3, 4, 5, 6, 7, 8, this is our potential energy. And then across the x-axis is our spring stretch. Now that dashed line, let's read for clues. It says a 4-kilogram mass is attached to a vertical spring. So we're vertical. In your head, imagine maybe the spring is on the ceiling and we put it, and it's going to move up and down, up and down, up and down. It says the total, our unknown force spring constant. So question mark K. We'll solve for it, but we don't know it here in the beginning. The total potential energy in joules, we're talking elastic spring and gravity, is shown above as a function of the spring's stretch in meters. So everybody's SI units, that's good. But the important thing to know is this total potential is the gravitation plus the elastic. That's what's being plotted. It's not just one, it's the total potential. The dashed line at 6 joules is the total mechanical. What's mechanical energy? Refresh my memory. Kinetic plus, and I'm going to split the potential into both. And so at any given point, and always neglect friction, air resistance, right? We'll keep our conservation until told otherwise. And so at any point on this graph, our total is 6. But there's parts of the graph that go up to 7 joules, 8 joules. Is that possible based on what they've told us? The total is 6, designated by the dashed line. And so basically we get to ignore anything above the 6 joules, okay? Now, before I answer questions, what's the max speed? What's the force constant, spring constant? And then the others, let's spend some more time getting to know what the situation. There's special places on the graph. There's special places for simple harmonic. Would you agree that 6 joules, when plotted, this is a maximum potential energy? What's the kinetic energy if all your mechanical is in the form of potential? 0. So I'm going to come down here to the 0 joules and say KE right there. I'm going to plot a kinetic energy graph just to help make sense. Then look at stretch equals 0, where it crosses the y-axis. Again, it's a total potential plotted at 2 joules. How much is left for kinetic? 4. And then what's the other special place in simple harmonic motion? Equilibrium. Now, they don't tell us where it happens, but equilibrium has a maximum kinetic. So how much is left for potential? 0. On our graph, where does that happen? At 0.1. So about 0.1, we would have a KE max. And then hopefully you see it's going to kind of reverse going to the other side, right? And so about right here, we'll have 0. Now the 4 is kind of harder to tell, but maybe about right here. By the way, when you draw graphs on the AP exam, they'll give you grid lines. If they don't, they're just looking for a sketch. So how are we going to connect these kinetic energy plots? Straight line? Curvature, it's mirror image of the potential energy. Hopefully you remember that from the simulation. And why am I doing it if they didn't tell me to? Hopefully it helps, right? If you don't draw it, you still have to think about it. Everybody good? Okay. A, what is the maximum speed? Well, wouldn't it be helpful to know the maximum kinetic energy? Which we now know to be what? 6 at some point. And so this is going to happen at equilibrium. That's our fun fact. And so maximum kinetic equals that 1/2 m Vmax squared. So we just said maximum kinetic is 6 joules. They give us the mass of 4. And so let's see, 1/2 of 4. 6 divided by 2 is 3, right? And then we got square root. What's square root of 3? I really don't remember. 1.7 meters per second. Everybody good? What is the force constant? What's the spring constant? Force constant, spring constant, same thing. Little k, what's little k for the spring? How are we going to figure this out? Well, at equilibrium, what do we know? What's our physics knowledge? When it passes through equilibrium, what equals what? So at equilibrium, for a split second, this is not constant, but for a split second, the net force on the object is 0. Well, again, your picture, you got a vertical spring with vertical gravity. Isn't there 2 forces acting on it? And for the net force to equal 0, those 2 forces have to equal or 0 out based on summing. And if you're saying, well, you didn't do that on the pendulum, right? Remember, pendulum is swinging in a circle. This one's not. It's just moving straight up and down. For this moment, these 2 forces are equal. And so put in Hooke's law, spring force equals Kx, weight Fg equals mg. So to solve for K, mg over x. Mass, they said, is 4. Gravity will go with 10. Wait a second. Do I know the stretch to equilibrium? It's in the graph. You got to go read the graph. They plot stretch distance. So we've already identified the equilibrium location. How much is it stretched? 0.1. Now, careful here. What do we get? You can move your decimals. 400 newtons per meter. Good there? All right. I think 3 more questions. Now, before we go over C, just to kind of get in the mindset, I want to remind you of 2 things. Remember with the pendulum, remember with the other spring one that we've done, we decided 0 meters. We picked the lowest point. Does it have to be the lowest point? Could it be some other spot? Sure. And then the other thing I want to remind you of, let's think back to chemistry. What if I give you some salt and I say, go get the mass of this cup of salt? Well, usually you need to know the mass of the cup first, right? So you can put the cup on the scale, but you don't actually need to know that mass. You can hit a special button, the 0 button or the tare button. And it says, okay, you want to ignore the mass of the cup. You just want the mass of the salt, right? So keep that in mind. Where is the gravitational potential energy zeroed we're not really being asked, where do you have zero potential energy? It's where do you hit the tear button? Where is it reset, if you will? Where can we say, okay, here is our 0 point? Does that kind of make sense in rephrasing the question? And so up above, that graph is a potential energy, but remember it's a total, okay? And so we want to get rid of the elastic potential energy. We don't want it to mess things up. Where do you have 0 elastic potential energy and only have gravitational? Say again. When the stretch is 0. And so right here, when your stretch is at 0, then we know that this 2 joules is only gravitational potential energy, okay? And that's the special spot we're going to use to figure out, well, where do you hit the tear button? Where do you reset? And so where the stretch distance equals 0. And so gravitation is in the 2 joules. And of course, gravitational is mgh. And so 2 equals, our mass was 4, gravity's 10. And this height, this position in the vertical is where we're basically going to say 0. But we don't calculate 0. Hopefully you see that. And so we get 2 over 40 or 1 over 20 or 0.05, I believe, meters. Okay. Okay. Last 2, I think, should go pretty quick. D, can the mass reach the point of stretching 0.3 meters? If we go up to the graph, 0.3 meters is where? Well, it's the end of the graph. And, it's in that region that we said wasn't possible, right? You would need 8 joules, but what's our total max? 6. And so, no, 0.3 meters requires or needs 8 joules, but 6 joules is the max total mechanical energy. Okay. E, what if friction was introduced, right? And so whatever form of friction, mainly probably that air was damping. By the way, here's a vocab word for you. Damping is basically the friction of oscillations, okay? Have y'all ever seen these French doors? Do you know what a French door is? Okay, it doesn't have some kind of system to make it shut. It just, you open it and it goes swing, 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 swing. Eventually it damps out, right? Now that's the opposite of what you want in a car. When you drive over a speed bump, do you want to sit there and go bounce, 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 bounce? No, we want to minimize the bounce. We want good shocks, right? That's all damping, okay? It can be a good thing. It can be, I guess, not a good thing. But here, what if damping occurred? If we turned friction on one of those sims, where would the mass be located once it eventually stops? We know this. At equilibrium, its resting place. Okay. Resting place, happy place, whatever you want to call it there. Good deal? All right, next time, because I definitely don't have enough time, look at page 6. In 2018, this was a free response. Now, it is a paragraph response, but here's what you can expect on the May exam. This one is a triple topic. There's going to be a collision. If there's a collision, what topic do you probably need to use? Momentum. There's a height change. There's a spring. You're going to have some energy. And the first question is about period. It's going to oscillate, okay? So it's simple harmonic motion, it's energy, it's momentum. Triple topic there. So we'll do that one as well as a couple other NIMSYs. We only have one class left before the exam or quiz, that assessment next week, okay? And so I am here in just a little bit, or if I forget, I'll do it tomorrow. Practice quiz for you on campus. It's going to be, short. This is a shorter topic. And so you have extra practice here in the packet. There's some multiple choice along the way. Okay. Some old other free response questions. Okay. Let me know if you have any questions.